on some of those calculations, or while we're having the talk on this new topic, go ahead and try to finish those calculations or finish your design for the tensile testing that we'll do in a few minutes. Today, we're going to talk about stress again, but we're not going to say we were lying. We were just going to say that we hadn't told the complete story, okay, in terms of predicting when something might fail. Okay. So we're going to discuss finding a condition of triaxial stress and what that means. So here's kind of a foreshadowing figure. Remember yesterday we talked about how, or actually before yesterday too, we talked about how when you get the maximum in-plane principal stresses, you get zero shear stress. You can find some orientation that will allow you to find that state of stresses. We're going to say this is actually generalizable to 3D. You can find a state of zero shear stress in 3 dimensions as well, where you will have 3 principal stresses, sigma 1, sigma 2, and sigma 3. Okay? We'll then talk about the absolute maximum shear stress using Moore's circle. What does this mean? Well, we get to draw a couple more circles on the tau sigma graphs. And then we'll talk about some examples. Okay? And we won't spend the whole time here. We're going to go to the lab in I guess probably in an hour. We'll see. So once again, here's the general depiction of stress and the general definition of a tensor. Okay? And we, for the last couple of days, have been thinking mostly in 2D, right? We've been thinking about an XY plane, which could be expandable to an XZ plane or YZ plane, okay? And we've kind of tried to simplify our tensors to pretty much only consider a 2x2 scenario. And this is fine in many cases, but when we think about failure, we want to discuss what's happening in a 3rd dimension as well. Okay? So to discuss this idea of triaxial stresses on a 3D element, we will start with a state of stress on a 3D element. Okay? So maybe it's something that looks like that. There's a sigma x, sigma y, sigma z, and there's a tau xy, tau xz, tau yz. Okay? And so to define that state of stress, you need 6 components. Then and so we can fill up the tensor like that. All right. Then we think, all right, we need to reorient this element in some way so that we can predict a new state of stress. Okay, and we got some tools for doing that. And if you have a tensor, the way to do it, quite frankly, the easiest way to do it is to use that R. Do you remember this? So if you have for a 3D tensor, right, the simplest way to come up with a new state of stress, if you know the rotations, is to use R times sigma times transpose. Yeah, that's the simplest way. And what's weird here, though, is sometimes you end up having, or you're wanting to do kind of a couple of rotations. So you do one rotation about one axis, and then you do another rotation about another axis. Okay, but that can be captured in a rotation matrix. The rotation matrix ends up being the matrix multiplication of those two rotation matrices that you've created, right? Because you remember we said, hey, this is the rotation matrix for rotation about x, this is rotation about y, this is rotation about z. Okay? Typically, we've been looking at xy planes, so our rotations have just been z rotations. Okay? But anyway, we can find an orientation that will only have normal stresses, and this is the state of triaxial stress. Okay? So what are we ending up looking for? We are looking for an element that looks like the one that we showed on the previous slide, where you have sigma 1, that's typically the largest one, sigma 2 typically the next largest, and sigma 3 typically the smallest. And what would the tensor look like? Well, the tensor would look like this. 0 shear stresses. Okay, just sigma 1, sigma 2, and sigma 3. Now, I won't make you do a generalized 3D state to triaxial stress. That's a little bit complicated. But here's how you do it if you're bored on a Friday night, okay? What you do is figure out these components, I1, I2, and I3, okay? And these are called the invariants to an eigenvalue problem, okay? And so I1 is sigma x plus sigma y sigma z, and we're not really going to go into why this is, and in fact, when you take DMC, you probably won't go into why this is either, okay? But this is a procedure. This is how you do it. And once you've got I1, I2, and I3, and these are not, the second moments of area, right? These are just these invariants. You create a third order polynomial with the appropriate coefficients, and then you solve for the roots. Okay? So you can use MATLAB, you can use whatever your favorite solver is to figure out what the roots would be for this third order polynomial. And a third order polynomial potentially has 3 roots, right? It has 3 roots. So those 3 roots will be the sigma 1, sigma 2, and sigma 3 for a state of triaxial stress. And that's pretty nifty. This technique doesn't tell you the associated rotations that are necessary to get to this state of stress. It just tells you these are the magnitudes of sigma 1, sigma 2, and sigma 3. Okay? And if you want to know what a tau 1,3 would be, a tau 2,1, a tau 3,2, okay? You could figure it out using these equations. Now, but this is the state of principal stress, right? So, what are we talking about here? And this is going to be a little bit, right? There's no overall shear stress, right? Okay, we're not talking about what is the tau x prime y prime, the tau y prime z prime, the tau x prime z prime. We're talking about something a little more abstract. We're talking about, well, maybe it's less abstract. Okay, that's probably debatable. We're talking about maximum in-plane shear stresses. So what does that mean? That means, okay, let's just say, for example, that you have sigma 1 equal 100 megapascals, sigma 2 equal to 50 megapascals, and sigma 3 equal to 0 megapascals, all right? And I say, that's the state of triaxial stress. And you're like, hey, that's awesome, okay? So if I'm doing my criteria for, or looking at criteria for failure, I'm trying to pick out which of these criteria is going to be my best criterion to determine whether or not I fail. If you say, oh, if I'm just using maximum normal stress, Well then, bing, bing, bing. This is the person, right? That's the one that's most of most concern, because that's the maximum normal stress, 100 megapascal. But if we think about it, if I start looking at different combos of planes, if I look at the 1-3 plane, or the 1-2, or the 2-1, or whatever, if I look at a different plane, right? If I drew these three like this, right? I would have a point here, a point here, and a point here. This would be my sigma 3, this would be my sigma 2, and this would be my sigma 1. And if I look at those planes, wait a second, there is, even though this is this like magical state of no stress, no shear stress, and it's not magical, okay, but maybe I should say mathematical. Anyway, the maximum shear stress, I could take a look at one of those planes and I could kind of rotate such that I could find my maximum shear stress. Okay? Because I would start off like this, sigma 1, sigma 2, sigma 3, and then I'd say, oh, but you know what? If I take those two stresses, I can rotate 45 degrees and find maximum shear stress in that plane. Right? So like if I had 1-2 plane, right, whatever that x prime is 1 and y prime is 2, and then I rotate sigma 3, right, about sigma 3, 45 degrees, then I would find these maximum shear stresses. So that's what this is telling us right here. See this? Okay? And maybe those are the ones that I'm concerned about. Okay? Maybe. Or maybe it's this other circle that emerges between 1 and 3. Okay, and we're going to talk about that. And this is like what we're talking about when we say absolute maximum shear stress, right? Because there are now 3 combos that we have to think about. We have to think about what's happening between x and y, what's happening x prime y prime wise, what's happening x prime y prime z prime wise, and what's happening x prime z prime, okay, or 1-3. And hint, hint, 1-3 is usually the one that we're concerned about, because that is the maximum normal stress and the minimum normal stress, and that's going to lead to a high shear stress. When I say we're normally concerned about it because many of the materials that we deal with in this course are ductile, and shear stress is what kills us, right? I'll just, there's sometimes, I wonder if I should talk about failure. I almost think, maybe I should move failure criteria up earlier, because I keep foreshadowing when we get to failure criteria, okay? The shear stress is important for the ductile materials. I don't know how many times I say that. And when we get to failure criteria, the normal stresses are important for the brittle materials. Okay, so if we want to find the principal stresses, okay, or the state of triaxial stress, this is how we might do it. For, let's say, a sigma x equals 100 megapascals, sigma y equals 50, tau xy equals 10, all right? So we can go ahead and, kind of do a little bit of rotating around, okay, and we can figure out what we might have for the sigma 1 and sigma 2, right, like this, okay. And if the other stresses are 0, we're fine, okay? Because all we have to do, well, let me ask you the question, okay. So, it wasn't a really great generalized example of 3D stress, right? Because what's happening? Tau yz, tau xz are 0, and sigma z is also 0. Okay, So we can just use our techniques that we already have for making more circle, or finding the rotation to find a sigma 1 and sigma 2. What is sigma 3 here though? What is sigma 3? Yeah, it's just 0, right? Because sigma 3 is equal to sigma z. Alright, and that's 0. Okay, so we now so if we rotate the elements by 10.9 degrees, as we see there, okay, that will get us to the state of triaxial stress. Okay, and sigma 1 will be 102 megapascals, sigma 2 is 48 megapascals. And there's 0 shear stress, okay, on those faces. But you can still find a maximum in-plane shear stress on, say, the 1-2 plane, or the 1-3 plane, or the 2-3 plane. The other way to do it is to solve the eigenvalue problem. Okay, so if you like, you can use Python to do this, or MATLAB to do this. Okay, however you like to do it, and it will tell you that. Do you have to do that for the exam? No. But would you have to do this on the exam? Yes. Okay. And the other way is to find the roots, okay, of that equation. So either way. Any questions on this? Okay, so what we've talked about here in this part is how to find the normal stresses associated with what's called a triaxial state of stress, where you have no shear and it's just sigma 1, sigma 2, sigma 1, sigma 2, and sigma 3. Now, if we have sigma x equals 100, sigma y equals 10, 100, sigma and tau xy equals 100, okay, you have an opportunity to work on that question. That one, you can, for the homework, you can use the invariance. So just use the collab, essentially. All right, you don't have to do it on an exam, but you can do it there. Or, you know, this is a 2D problem in a sense because the other stresses are 0. The tau xy, or tau yz and the tau xz and the sigma z are 0. So you could just use more circle as well. Okay, but that's what you're going to be looking at. And then if you have all 6 components equal to 100 megapascals, all right, then the question is, what will be your kind of final answer, all right? And this one, go ahead and definitely use the collab for this, all right? And this answer might be kind of interesting and fun. Okay, maybe, I don't know. You maybe have a weird idea of what fun is. Okay, but it's like, oh, that's interesting. Why is that? Well, we won't necessarily discuss that, but you can see what the answer is. Okay? Now we're going to shift gears and we're going to talk about absolute maximum shear stress, which I kind of already talked a little bit about, but now we'll talk about it formally. So let's say that we have this, sigma 1, sigma 2, and sigma 3 is equal to 0. All right? We draw it. It's beautiful. All right? There's no shear stress. I mean, who likes drawing shear stresses more than they like drawing normal stresses? Probably not. I mean, you had to do 4 arrows instead of 2 arrows. You have to think about 2 subscripts instead of 1 subscript. But anyway, so there's 0 shear stresses here in this plane. Now, what happens with a Moore circle, okay, for this diagram? Well, you've got a sigma 1 and a sigma 2, And this is supposed to say, oh, I'm trying to make it red over here, and this is the red circle. We agree on that? All right, we've been doing this now for a day. More circle. Okay. So if you were to say, you know, and just as a review of more circle, what is the maximum in-plane shear stress there? Just as a review. Yeah, Dylan.
Be sigma 1 minus sigma 2 over 2.
Right. All right. It's the diameter is the sigma 1 minus sigma 2. The radius of that circle is going to be half of that, and so top or bottom is what you just said. Quantity sigma 1 minus sigma 2 divided by 2. Okay. Now, what happens if we instead take a look at the zy or the yz? So what have we done here? We have rotated this such that now x is going into the board and z is going to the right. Do you see that? We took this element right here and we just rotated it. So now that z points to the right and x is into the board. So now we're looking at what? Well, a zy plane. Okay. So looking at the zy plane, right? Ignoring, you know, we're doing our 2D stuff here, kind of. We don't see a sigma 1. Right? All we see is a sigma 2. So in this case, right, and or we have a sigma 3 which is equal to 0, right? We have sigma 3 equal to 0 and we have sigma 2. So what's that more circle look like? Well, it looks like this one. Oh, sorry. This one. See that? Okay. So that's the Moore circle associated with the YZ plane. What's the shear stress, maximum in-plane shear stress here? Well, it's going to be the same thing you just said, right? So sigma 3 is equal to 0, so it's going to be sigma 2 divided by 2. Okay. And you know where this is going. We're going to now look at another state of stress, okay, where now we take the first, let's see the easiest way to do it, right? And say take this first state that we had and we rotate it so that sigma 2 now goes into the plane or into the board, right? So x is this, this y coordinate system is going into the board. All we see now in this planar view is sigma 1. We see sigma 3 as well. Okay, but now this Moore circle, okay, is going to be going between the sigma 1 and the sigma 3. Any questions on this? Okay. So yeah, we can identify our individual maximum shear stresses, but there is now the absolute max. Right? The absolute max is the one that's going to be associated with the sigma 1 and the sigma 3. So when we think about whether or not the material might yield due to a shear stress, we look at the absolute maximum shear stress. Now this is a case where 3 principal stresses are at 0 or to the right. Okay. What might happen if you have some principal stresses that are not positive? Okay. Or what happens if you have, 3 principal stresses that are like not one, then one's not a 0, right? You have like a sigma 3 that's actually non-zero. Okay, it could be to the right, it could be to the left. Okay, so sometimes you have to think about these different types of circles. So here is a case. We have our sigma 1 positive and our sigma 2 negative. And this is where I said, well, sigma 1 is greater than sigma 2 is greater than sigma 3. Usually in mechanics, or a lot of times in mechanics, we get a little bit loose with this idea, right? And we'll say sigma 3 in this case is 0. Sigma 2 is negative, so it's actually less, right? But it has some magnitude, so we still associate it with sigma 2. Okay, so often sigma 3 just ends up being the 0 at the origin. So when we draw this one out, right? Sigma 1 is going to be over here. Sigma 3 is going to be over there. Sigma 2 is going to be over there, not sigma 3. And sigma 3 we'll say is at the origin. And so this is now the Mohr circle associated with this plane. If we look at rotating the element, okay, so now what do we do? Z was coming out of the plane. Now we've rotated it about the, actually, which way did we rotate it? Well, we could have just rotated it about the x-axis, okay, but instead what we did is we rotated it about x and y, okay? But anyway, we can get rid of the sigma 2, all right? And when we do that, now we have two stresses. We have a 0, so like the sigma 3, and we have the sigma 1. Okay? And you can also imagine another state of rotation where we're looking at, we only see a sigma 2. And we only see 0 like this. Okay? So in this case, what is the absolute max? Well, it's already here. It's going to be sigma 1 minus sigma 2 divided by 2, right? So in this other case, we said it was sigma 1 right, so it was just sigma 1 divided by 2, right? Or sigma 1 minus sigma 3, quantity all divided by 2. Okay, and in this case, it's going to be sigma 1, quantity sigma 1 minus sigma 2 divided by 2, like that. Okay, any questions on this? Any questions, any thoughts? Yes, Joshua.
I noticed that the stress is positive even though it's in the negative x direction initially. So it's just based on the direction relative to the face.
Right. So yeah, again, I probably took a little bit of liberty here, right? I'm trying to show that it's a compressive stress, and I'm kind of trying to eat my cake, whatever, into something another cliche if I can't remember. Yeah. So yes, what I really, more technically correct would be what you've just pointed out, that I draw sigma 2 going out, and then I just say sigma 2 is less than 0. Right? Or, it's not horrible to do it this way. If I say, okay, it's compressive and I know sigma 2 is a positive number, but when I draw on the Mohr circle, I know it's negative.
And so what if you had two outward normal forces on the x direction, but they're on the opposite faces? Then would that mean that the sigma x would be those two stresses added?
Okay, so I don't know if I understood that question. Are you saying
Follow.
if you had stress here and a stress here, and then what's next?
And would it just be effectively added?
Yeah, right. So yeah, you still yeah, okay, good. So remember, even in the last exam, we learned how we could add normal stresses to each other. We learned how we could add shear stresses to each other, right? Because you could have a transverse shear stress and you could have a torsional shear stress, right? And they could potentially add to each other. Or last sessions, right? And yeah, you can have an axial load, right? And jumbo sitting, right, on a pressure vessel, but that pressure vessel is pressurized, right? And so you have those axial stresses counteract from each other. Yeah. So whatever the net, you want to, when you start drawing these more circles, you want to already have figured out all the superposition, all the combined loading and stuff, and you want to get, yes, these net or these effective stresses on the entire element. Okay, does that make sense? Good. Okay, so now, if we want to look at the absolute maximum shear stress with this example that we kind of had previously, we have a sigma 1, 100, sigma 2 is 50, sigma 3 is equal to 0. We do the Mohr circle, and you just put the points down. So the 100 megapascals, the 50 megapascals, the 0, and you draw 3 circles. Like that. Okay? Yes, Isaac.
So let's say when you find like the radius,
Yeah.
are you using like the middle or you just find the radius for both of them?
So they're all circles, right?
Mm-hmm.
Even though my circles are crummy looking sometimes. Okay? So they're all circles, so those 2 points, but I need 2 points to define each of those circles, right? On the circle. So those 2 points, they're 180 degrees from each other on the x-axis, so they're going to give me the diameter. And I'm going to take the diameter and just divide it by 2. Does that make sense? So they're not, no. So this point right here is not necessarily, in many cases, it's not the center of this orange Mohr circle. In this case, it is, right? Because it's 150 and 0. But if I had done like 120 megapascals, 100 megapascals, 20 megapascals, and 0 megapascals, I would have gotten the same absolute maximum shear stress. But, you know, this circle over here would be smaller, and it'd be over here, and this circle would be larger. Okay, does that make sense? All right. Okay. So the absolute max is going to be the 50 megapascals. Okay, so then you have a question, right, where you have like a negative compressive stress, and you have 100 megapascals of positive axial stress, right? And or something similar to that. And then you could have something where you have a sigma x, a sigma y, a sigma z, that are where the sigma z is non-zero, but you know how to handle that too. Again, just put the 3 points on the x-axis of your Mohr circle, and then start drawing circles. Okay. Yes, Andrew.
So in here is sigma x, sigma y, sigma z, are those all the principal stresses?
Yeah. So yes, so that's a good observation. What we're looking for is the in-plane, the maximum in-plane shear stress that ends up dictating the absolute maximum shear stress for this system. Yeah. Okay. Yes, Dylan, what's up? What were you gonna ask?
Never mind, I was gonna say something about that last problem.
Yeah, go ahead.
Could you just take the maximum normal stress and then the minimum normal stress, find the difference, then divide it by 2?
That's what it's going to be, right? That's what it's going to be, yeah.
Okay.
Yeah, that's what it's going to be. Okay. Draw the circles, though. It's fun. Draw the circles. Great. So this is supposed to be with some structural examples. Okay. So remember we talked about the sphere yesterday? I guess I already spoiled this problem, right? Where if it's a sphere, we said that we have just sigma 1, sigma 2, whatever. They're going to be represented by a point. Remember this? Maybe I didn't spoil completely. Okay. So I do that. So in that, if I said, what is the maximum in-plane shear stress for this particular orientation that I've just drawn, what would you say? Say 0, right? But now we go 3D, right? And what do we say? Sigma, we have a sigma 1, sigma 2 that are equal to each other. But sigma 3 is
0.
0. So, so the absolute maximum shear stress is not 0. Okay? The absolute maximum shear stress is going to be PR over 40. Okay? Everyone see that? This is a pretty significant result. Okay? And it goes back thinking about the geometry. Yeah, I can, if I'm on a sphere, and I'm looking at the, axis coming out of that sphere through my body, I can rotate anywhere, and all I see is, I just see the same normal stress, right, as I rotate around. But then, if you are looking at me over there, and you're like, actually, no, I see a different perspective. I see that you have 0 stress now in this, in your direction, right? And I see that you've got an axial stress coming out like this. Then in that particular plane, yeah, I can think of a maximum in-plane shear stress. Okay? So this is kind of a classic example. Okay. If you're dealing with a cylindrical pressure vessel, of course, the in-plane shear stress that you're dealing with, is not going to just be a point, right? You're going to have a sigma 1 that's different than sigma 2, and then you have a sigma 3. So then you get to figure out what the absolute max will be. You already know it's going to be whatever the difference is between that maximum sigma 1 and that 0, which is 0, okay, divided by 2. So it's going to be that sigma 1 divided by 2. All right. Now, question 6 is going to say, hey, go back to section 16, okay, and you're going to look at the state of stress that you came up with there, okay, which is a 2D state of stress. It has some shear stress, remember? Actually, did that one? Yeah, let me just look. Oh, yeah, because this has like 3 loads on it. All right, so it's going to have some shear stress, it's going to have some normal stress. So take a look back at that, and then you can figure out what the absolute maximum shear stress is there. Yeah, that's right. So this is all that stuff. Yep. All right, and then we have these 2 quantities right there. Okay. So that's going to give you the. There was no sigma y, right? There was just no sigma y, but there is a tau xy. Okay, so in that case, what do you have to do? What's the procedure here? Yeah, Joshua.
You use the eigenvalue.
Okay, you could use the eigenvalue thing to. What would the eigenvalue cross? What would it tell you?
Like plug in I1, I2, I3.
Okay,
And then
and what would it tell you in the end? No, this is not the way I would do it, but this is a viable way to do it. So what would it tell you? Shane?
principal stress.
It would tell you the principal stresses, right? So let's just say you do the eigenvalue thing. All right? I like that. Do the eigenvalue thing. All right? So if I do that, we're going to get, and I don't remember if these are positive, negative. I mean, I don't remember what the values are, but let's just say that they're, well, I know what sigma 3 is. Sigma 3 is 0. Okay? I don't remember I don't remember where these other, but let's just say that those are the other two. Okay. If you've done the eigenvalue thing, then you'll get these 3 points. Okay, one of them should be 0. And, you know, you can start drawing your more circles like that. That's a really bad example, right? So that's one way to do it. What's another way to do this problem without doing the eigenvalue? Yeah.
To the more circle, just like one circle.
Right.
Find the
Yeah.
principal.
Yeah. So in this case, right, you've got this weird predicamento, all right, where you've already got something that's going to give you, you know, 0 here. So sigma 3 we already know is here. Okay. Sigma 2, or, well, actually I should say, what is sigma y in this case? Sigma y is also equal to 0. Okay. So that's going to put 2 points there. All right? And you know what sigma 1 is. Well, do you know what sigma 1 is? You don't know what sigma 1 is yet, right? What you do know is that this has some more circle where this is, and again, I can't remember if these are positive or negative, but let's just assume they're both positive. Okay. So sigma x, and this is going to go through the origin because it has to. No, it doesn't. Sorry, it does not. Sorry, it does not. I'm sorry. That was a lie. Okay, do you see this? This is a little counterintuitive. Remember, sigma y is 0 in this case. And we can say that's got the minus tau xy associated with it. So this, the Mohr circle actually goes like this. So whatever the maximum in-plane shear stress, assuming that sigma x and tau xy are both positive, whatever the maximum shear in-plane shear stress is for this Mohr circle is going to be the absolute maximum shear stress for the system. Because these circles are going to do like this. Like that. Did that make, I think I went a little fast. Did everyone get this idea? So, okay. So what is go back to what is the general process for creating a Mohr circle?
You find the center,
Yes.
you plot your reference point, you find the radius between them, and then you can construct most of the rest of the circle.
Correct. Okay. So where is this circle? Where is the average? Okay, so give me a quantified number. The average is just going to be sigma x divided by 2, right? Because the state of stress here, there's no sigma y. Sigma y is equal to 0. Right? So sigma y is equal to 0. Right? So sigma average is equal to sigma x divided by 2. Okay? Now, that actually could be enough to tell me almost everything I need to know. Because, no, it's not enough. I do need to figure out the radius with the tau xy. Yeah, you have to figure out the radius with the tau xy. Okay, so how do you figure out that? You figure out that radius by using Pythagorean's theorem, right? So you figure out, okay, what is this? This is going to be sigma x minus sigma average in that direction. And this right here is just the tau xy. Like that. So the radius is going to be the square root of this quantity, sigma x minus sigma average squared, plus tau xy squared. That will be the radius, which actually ends up being the maximum absolute maximum shear stress as well. Sigma 2 is going to be somewhere just to the left, right? Because this circle, it has to the Moore circle for this plane has to go through this point and this point. So it has to go to the left. Sigma 2 is going to be to the left. Does that make sense? No, it didn't make sense. I see confused looks. Let's see. How else can I explain it? What? Go ahead.
Sorry, can you clarify again where you got the two smaller circles? Which one is which?
Okay, so the two smaller circles I drew in kind of after the fact. Okay. Sigma 3 okay, so first off, do we agree that sigma y is equal to 0? For this. Does everyone see that? That's just because it's not specified. When we did the calculations, there was no sigma y. Okay, so there's no sigma y. So sigma y is equal to 0. I don't know sigma 1 yet. Okay, because I wasn't given a state of principal stresses. Right? I'm given this like, there's a tau, unfortunately, right? There's a tau and there's a sigma x. Okay? But I do know that sigma 3 is going to be equal to 0. Why do I know that? Because I've been given a plane and there's nothing coming out of it. Right? So I know sigma 3 is equal to 0. Okay? So now what I got to do is I got to go and figure out what sigma 1 and sigma 2 are. And to figure out sigma 1 and sigma 2, I had to draw a Moore circle, or I get to draw a Moore circle. So to do that, I want to figure out where the center is, like you said, all right, and that I can figure out by taking the average of sigma x and sigma y. Okay, and then I can plot that point on the Moore circle, which is going to be based on my sigma x, where that is, right, and my tau xy. Right, I just plot those. I plot that coordinate point, not even using a circle, just based on what sigma x and tau xy are. Okay. And remember, if I go 180 degrees on a Moore circle, that's like going 90 degrees, and sigma y was equal to 0. So sigma y has to be on the y-axis, or on the vertical axis. Okay, well that wraps up this part. We're going to go to lab. All right, any questions, any thoughts on this? Did this blow your mind? Maybe, maybe not. Absolute maximum shear stress. Okay, states triaxial stress, or state of principal stress in 3D. All right, being able to calculate these things quickly now gives you even further tools to be able to figure out whether or not something is going to fit. All right?